Recording it. Okay, great.
Uh, Let me see if I can share. Let me know if you can see something.
Yes, I can see the screen here.
Do you see this page of linear algebra?
Yes, let me make my screen bigger. Give me 1 second.
I will also make it a bit bigger. You can see better. Okay.
Yes.
Yes. So last time we were discussing this linear model, y equals x beta plus epsilon. So that is our that is the starting model around which all machine learning models will be benchmarked. So any model that you ever work on should not be worse than this. Okay. So that is like the baseline of all models that we use. And for linear models, we usually there are multiple methods as we discussed for estimating the beta parameter. Easiest is you minimize the sum of squares, which gives us this is least square estimate of beta, like the familiar formula x transpose x whole inverse x transpose y. And then if you plug in this formula for y, you get the fitted values, which is like the expected response, like from the model based response. And we introduced this hat matrix as a notation, and then we derived a little bit about what the hat matrix does. And we also said that we have this kind of property that y minus y bar whole square, so total sum of squares, can be written in terms of explained sum of squares and unexplained sum of squares. So that is the idea, and our beta choice is such that the unexplained sum of squares is as low as possible. We cannot make it zero necessarily, but we have made it as low as possible. And then we also discussed like what if we assume that the errors are normally distributed, and then we have a likelihood function, and it turns out that minimizing the likelihood is same as minimizing the sum of squares. So you get same solution for beta. So you don't have to remember two formulas, the formula remains same. But the additional thing is we have an estimator for sigma square, and we also have some expectation and variance of those the beta estimate. And the nice thing about this estimator is the expectation of beta is beta, beta hat is beta. So and variance of beta hat is this matrix sigma square q d power minus 2 q transpose. And then we discussed a little bit about what does this d power minus 2 mean. So remember that the d is the matrix of singular values. So this is where we introduce the d.
Yes.
So
That's a diagonal matrix, right?
yeah, so that's a diagonal matrix and it contains all the singular values, and this P and Q are orthogonal matrices. So they basically just rotate things. D is the scaling part of the matrix.
Yes. That's the singular, that's
So,
the SVD right there, right? The one
yeah,
that,
that's the SBT right there. Yes.
yeah.
So when you do SBT composition, the P and Q plays the role of rotating things, and D diagonal matrix of singular values plays the role of scaling things.
Got it.
So when you have D power minus, we discussed that if D has elements like very large, let's say 100 or something, d power minus 2 will have very small elements. So the corresponding variance of beta will be very small, which is good for us. That means our true beta and our estimate beta will be close to each other.
Yes. Agree.
But if d happen to have one element which is very close to zero, then d power minus 2 will be very large. So that is actually bad for us.
I'm assuming then this is normally distributed. There's probably exactly the same thing we could do for all the types of distribution then as well too here.
We can accept two things. One, the algebra is not easy.
Okay.
And second, some distributions not necessarily even make sense so easily.
Right.
So you remember, I think you studied in your last semester a little bit of generalized linear model.
Yes.
Yeah, so that is basically if you change the distribution from normal to something else. Sometimes from those distributions like make sense only in specific cases. Like if you want binomial distribution, then your out response should be something which is a count kind of thing.
Got it.
Or Poisson. So those are basically your response would be counting kind of thing. And then the difference doesn't make sense in the traditional way. So the epsilon is y minus x beta, but the y is a counting thing and x beta is a continuously changing thing.
Okay.
So The interpretation is not that way. Rather, we interpret that y has a Poisson distribution whose mean is x beta. That way.
So this is the one
So
I should remember then, though. This is the most important one.
yeah, this is the most important one for continuous case.
Okay,
For discrete cases, we'll study the other logistic and all those things.
got it. Okay.
For continuous case, normal is the most important one. And we can do some more fun here, but let's basically a lot of things will revolve around some of the other methods, like other than linear model, like ridge regression and what's the other lasso regression. They basically are answer to like how do I solve this problem of D having small singular values.
Okay.
So they are trying to solve the problem of like practically how do I like manage this? Because it's one thing to say, okay, my variance of beta hat is large, so my estimates are bad. But is there a way I can improve it without changing the X matrix actually? So that's one of the directions we can go now. The second thing we can do is we assume that the variance of epsilon is sigma square into identity matrix. This means two things. One is that all the observations have equal variance, even though we need not know the value of the sigma square, but we are assuming it's equal for every observation.
Right. Which
And also we are assuming that they are uncorrelated.
they're uncorrelated too. Right. Yes.
So there are two assumptions. One
But
is
those are
equal
both
variance.
probably not correct in the real life, right?
Yes, in real life they may or may not be correct. So if so now it's one thing to say they are not correct. It's another thing to find out what's the correct thing. Like
Okay.
these two are not equally different questions.
Okay. Got
Saying something is not correct might be very easy. Suggesting what is the correct thing to do is might be more difficult. So sometimes like instead of identity, we can change this to some other metric. Then we can do the algebra and find out what is happening there.
Okay.
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 So that's another approach to go. So these are the two things on top of Emily we can do. But okay. So and there is a third thing to notice. When we do the linear regression, uh, how does the linear regression affected by outliers?
A lot, right?
Yes, but how?
The epsilon will be very large.
Is it necessarily? Okay, epsilon might be very large. Yes, I agree to that. It may not be sometimes, but okay, let's go with that.
But then your least square, yeah, right? Like your least squares will just blow up then after that. Your sum of squared errors will blow up.
Yes. So what will happen? The beta will change
Beta will change.
because you will try to like choose your beta which will minimize the sum of square, right? So if
Yes.
the
Yeah.
current value of beta is giving me a large sum of squares of error,
Yeah.
then I will try to change it something slightly different so that my sum of squares errors is different.
Yes.
Like it
Yes.
goes down a little bit. I will try
Yes.
my best.
Optimize for
So
that.
your
Yes.
beta will change, right?
Yes.
So a single outlier point
Can,
can influence the fitted line a lot,
yes.
potentially.
So do we, okay, maybe can I guess where you're going with this? Is there
Yeah.
a way to like not take the outliers into an account, but then we'd have to define what is an outlier then, right?
Yes. So I am not even going towards that. Like the step before is, can I measure how much influence a single point has? So for example, suppose I have a 100 data points.
Okay.
So ideally, each data point should have 1% influence over the result, right?
Right. So then some sort
It's
of
like a voting thing. Every person should have equal vote.
right.
But does the linear model gives everyone equal vote, or
Oh,
some
that
people have
so
undue
that's
influence?
where the lambda, so as we did the ridge regret, so that's where you're doing the lambda then. There's some sort of weight. That's what that means. Okay, got it.
Yeah. So the influence function, so the linear regression some points can have unusual amount of like high amount of influence. I just want to draw a couple of quick pictures to show you what that means, and then I will leave the algebra. So let me see what's my best chance of drawing the picture here.
from like a scatter chart or something.
Yeah, I want to draw a scatter plot. I just don't know how to. Let's see. Picture is not good. Oops. Yeah, I have no clue. Let's Google. This is nice. Yeah, let's start with this picture. So, so the idea is that suppose
Can we do
most of
something? Can you copy and paste this into the Word document then maybe just so that we have I have it.
let me create it there. It should allow me. Okay. Okay. Yeah. So the red line is for the linear model you get if
Yes.
you drop this one single point. There is one point which is way away from the all these points, right? Now the blue line is if you add this point, so you can see the line changes by how much. So it is like rotating the line. So that's basically the influence.
And all of your beta
Now,
coefficients have been affected a
yeah,
lot.
all your coefficients and everything will change. Your response line will change. So if you are trying to predict using this line, red line versus blue line, you will get entirely different things, at least away from the center.
And
Around the center will be,
that doesn't look like a very good predictor then. Wait, what is the center? How did you define that? How is
I
that?
mean, whatever is the average of the most
Oh,
of the other
average.
values.
Yep, yep, yep. Okay.
Yeah,
Okay.
some kind of center. Okay. So the idea is that the influence of this point is more because it is away from the center.
Yes.
So there are two things that increases the influence. One is you are away from the line fitted by the other, which is true for this point. The other thing is you are away from the center of the point.
Yes. So if it was
So
close,
if you are equally away from the red line, but you are somewhere around the center,
then it's
you
not that.
won't be able to rotate the line. You will just draw like pull it down a little bit.
Yeah. Yep. The
You won't be
line
able to rotate the line to so much amount. Yes, just pull it down a little bit, and that influence will be much lower.
yes, your beta coefficient doesn't change as much then.
Yes.
Oh, sorry. Are you at, there was there a question? I didn't understand.
No. I
Oh,
just wanted to make that comment.
okay.
And then there is also this very nice picture. Uh, let's visit this page and yeah. So this famous collection of four scatter plots is called Anscombe by Quadrat. So he designed this. These are four scatter plots of four different data sets, all of which fits to the same linear regression line. And in all of these cases, the x mean, y mean are same, correlation is same, but the scatter plots are way different.
Hmm.
So, like his moral of the story was that you shouldn't just look at the mean and standard deviation and all those things. You should actually look at the scatter plot before making any comment. So,
Hmm.
for example, the first one is a typical scatter plot that we see. The one just below that on the top bottom left, this is all the other points are on a single line, and you can see the influence of one point is moving it upwards on the right. So it's rotating a little bit, just one point which is very high. And again, it is away from the center, that's why the influence is high.
Yes.
Compared to that, the top right plot, it's not a straight line actually, it's a quadratic kind of thing. The points are actually in, and then there is a base fitted line which happens to match with this previous line.
Yes.
And the fourth one is most interesting. Here, like all the x values are almost same, except for one point, and the y values are random. And that single point is actually deciding the whole line. All the other points will give a vertical line. Like they will not have any say at all.
Yes.
So a vertical line would mean like I can predict only for one value of x. I cannot predict what will happen for other values of x.
Yeah,
And that single point is deciding, okay, so let this be the answer. That's why the line passes through exactly that point. Because there is no other information about any other point outside of that line.
got it.
So that's why this example of like different kind of influence different points can have depending on the data set, and it's actually good to look at scatter plots to do this. Now, if you are working in high dimensions, you cannot do this kind of scatter plots very easily
Right.
because you have to do scatter plot against each of the regressors.
Yes. Yes.
So people do that. People also look at all the plots between all the pairwise regressors. Like if you have 10 regressors, you look at like x1 versus x2, x1 versus x3, x1 versus x4, everything up to x9 versus x10,
Got it.
all the scatter plots.
Okay. Okay.
Okay, but that's like you can imagine like if you instead of 10 regressors, if you have 100 regressors, there's too many plots to look at.
Right.
So this is a real challenge when you look at high size data. Like how do you really be grounded in your machine learning? Because you cannot visualize things anymore.
Got it.
So that's the idea, and let's go back to our. Okay. So that's the story about influence. We can do some little bit of math later on. I'll see, find the formulas and all. Like I don't have them ready to derive and all that.
Okay.
You can calculate how much is the exact value of an influence of a point.
Okay.
It's relatively easy to do for a single data point. Sorry, single response. So simple linear regression kind of thing. But when you are doing with matrices, the expression will change.
Yeah. Higher dimensions.
Cool. Okay. So with that being said, let's move on to the other two regressions. So which people classify under penalized regression. Okay. So the idea of penalized regression is twofold. One is, I think we discussed a problem. Remember when we were discussing about null space of a matrix? Yeah. So the idea is that if you have a vector beta and then y equals x beta is your model. Now, if V belongs to the null space, then xv is 0, which means x of beta plus v is same as x beta.
Yes.
So then beta plus v is an equally good predictor compared to beta.
This is equally good predictor. Okay. Yes.
Because x into beta plus v is giving me the same output as x beta.
Yes.
And similarly, I can do beta plus 2v, 3v, any c times v.
Just because V is in the null space then.
Yeah, just because v is in the null space. And all this is happening from only one vector in the null space. If there are multiple vectors in the null space, then you can have more examples of like a whole collection of betas which will be equally good as a predictor.
Okay. Okay.
So your sum of squares of errors idea, or like I will choose the beta which minimizes the sum of squares, that doesn't work anymore because we have so many candidates who are equally good.
Oh, interesting. Okay. Yes.
Okay.
Yes.
So that means we need some way to like choose among the equally good people.
Yes.
If all your students are getting like half of your students are getting equal marks, you still have to like decide someone is the first guy.
Yes.
So that's what is happening here. So we need some kind of, so we choose based on some other second criteria, which typically is a penalty on the size of the beta. So the idea being that if two betas are otherwise equally good in predicting, we choose the one which has small coefficients, and small we will like define in some sense.
Okay.
Okay. So that is one idea behind penalizing. The second idea comes from this problem that we discussed here, where you have like the square of the inverse of singular values, and some of the singular values are small, so the variance is high. So what can we do about it?
Yes.
Okay. So both these problems are potentially solved by the penalized regression kind of thing. So what we do is we minimize the quantity to minimize the loss function is written as SSE plus mm, some function of beta. And this function is the penalty function of beta. Like the second part that we are adding, we call that the penalty function. Okay.
Hold on. I'm the
So earlier we were minimizing the sum of squares of error, right?
yes.
Now we will minimize this new quantity L, and that quantity is defined as sum of squares of errors plus some function of beta.
What is L? What would L be then?
L is a new quantity. L is a function of beta.
Okay, okay, okay. Got it.
Yeah, I should specify that.
Is that the loss function then?
Yes, that is the loss function.
That is the loss function.
Yes, and we minimize the loss.
This is a, can we pause on this one here and then can we jump to another meeting here? Because I think this is a good definition place. Can we just jump to the other one for 30 more minutes? Is that okay?
Okay, yeah, sure.
Okay, I'll stop this because I want to keep this as a good section
Would you
here.
be able to start a meeting?
I think so. Let me try, Sujay. I can message you if I can't.
Okay,
Then let me try.
okay,
Okay.
yeah.